All right, so this video is for motion problems in section 1.2. And so in this problem, really what we're going to be doing is we're comparing two different objects, usually they're people, and comparing how they move, okay? And so as we go through these motion problems, I just want to start by going through the three different scenarios that we're going to have. And it'll make more sense, I think, as we go through problems. But as we compare the two people that are moving, either they're going to go the same distance. And in that situation, when we get to writing an equation, we're just going to set one distance equal to the other. They could be going in opposite directions, in which case we're going to add their distances together. And then the problem will tell us exactly how far they end apart. And so we'll set it equal to that. Or they're going the same direction, but one's going farther than the other. In that case, we want to subtract their two distances. And again, the problem is going to tell us how far apart they are at the end. Okay, so just kind of make a mental note of those three situations, and then we'll take a look at each of those as we go. Okay. All right. So for this first problem, it says Miss Link and Miss Langford are traveling to a business conference. The trip takes 2.5 hours for Miss Link and 2.5 hours for Miss Langford, since she lives 40 miles farther away. Miss Langford travels 5 miles per hour faster than Miss Link. Find their average speed in miles per hour. Okay, so as we go through this problem, what I'm going to do is I'm going to create a chart, okay? Actually, let me back up a little bit. For all of these motion problems, the formula is a real common formula, which is distance equals rate times time, okay? So we're going to be using this formula for every single problem. And what's going to happen is we want to express the distance that each person travels as their rate times their time. And so even if we know the total distance that they go, which a lot of times we don't, but even if we did, in order to compare the two distances or to get an equation that we can solve, is we need to express each of the distances as the rate times their time. And so for these problems, it's common to use a chart. So let me kind of show you how this chart works. So in this case, we're going to have 3 columns. And I'm going to do rate times time equals distance. And there are 2 rows. And the 2 rows represent the 2 people or objects, but usually they're people, the 2 people that are traveling. And so in this case, we have Miss Link and Miss Langford. All right. Okay, so and now what we want to do is we actually want to fill in from the problem what we know about the rate and the time. Okay, so let's go back and read through that. So it says Miss Link and Miss Langford are traveling to a business conference. The trip takes 2 hours for Miss Link. So we know for Miss Link it takes 2 hours. And then it takes 2.5 hours for Miss Langford. So her time is 2.5. And then it talks a little bit about the rate, which it says Miss Langford travels 5 miles per hour faster than Miss Link. So we don't know either speed, but we know that Miss Langford goes faster. So if we say Link drives at X, then Langford's rate is X plus 5. Okay. All right, so again, those first 2 columns, we always fill in from the problem. The distance column, after we have those filled out, the distance column is always going to be just multiplying these 2 columns together. Okay, so Miss Link's distance is 2x, and Miss Langford's distance is 2.5 times x plus 5. Okay, and so every single time that we do these motion problems, what we're trying to do is we're trying to get an expression in rate times time for Link, an expression for rate times time for Langford. Okay. All right, so now we're going to go ahead and actually get the equation. So kind of go back to what we started for. Now we want to ask ourselves and kind of get an idea of what this problem is saying. Are they traveling the same distance? Are they going in opposite directions? Or are they going the same direction but different distances? Okay. Now, what's implied here is they're going to a business conference. So they're going to the same direction. It's not real explicit, but that we're going to take that for kind of what it's worth. But because Miss Langford drives farther, then their distances are, they're going the same direction, but they're going a different distance, okay? Now, who's traveling farther? Well, it's going to be Miss Langford, right? In fact, it actually says she's going 40 miles farther. So when we do the subtraction, we want to subtract Miss Langford's distance minus Link's distance, okay? So our equation is going to be 2.5 times x plus 5 minus 2x. And then we're setting that equal to how far apart are they, okay? Which is 40 miles per hour, or 40 miles. And that's the equation that we're going to use to solve, okay? So the whole purpose of the chart really is just to get to this equation, okay? So the chart allows us to figure out an expression for each person's distance. Then we have to go through and we have to set up the equation from there, okay? All right, so now if we go ahead and solve the equation, so we'll need to distribute the 2.5. So 2.5x plus 2.5 times 5 is 12.5. So as we combine like terms, I get 0.5x and then subtract 12.5 from both sides, gives us 27.5. And then 27.5 divided by 0.5 is 55. Okay. All right, now, that's not necessarily our answer. Okay, after we solve the equation, you've got to go back through and make sure you answer the question. It says find their average speed in miles per hour. Okay, so our answer is how fast each person is driving. Okay, so Ms. Link is X, so Ms. Link is going 55 miles per hour. And then Langford is 5 miles per hour faster. So she is going 60 miles per hour. And that's our answer. Okay. All right, so let's take a look at another example. Okay, so Dr. Strangelove drove to his grandmother's house for a weekend visit. He averaged 40 miles per hour driving there on Friday. Returning home on the Sunday, his traffic was lighter, so he was able to average 48 miles per hour, and his driving time was 1 hour less. What is the distance between Dr. Strangelove's home and that of his grandmother? Okay, so I'm going to go ahead and create my chart. So rate times time equals distance. And in this case, it's the same person traveling, but there's two instances. He's traveling to his grandmother's home, and then he's traveling home. Okay, so I'm just going to use those to describe it. Okay, so go ahead and fill out the rate and the time based on what's given to us in the problem. Well, in this case, we actually know the exact rates. Okay, so we know he drove 40 miles per hour there, then he drove 48 miles per hour home. Now for the time, we don't know, but we know that driving home was 1 hour less since he's going faster. So if we say that going there was X, coming home is X minus 1. Okay. Now, alternatively, you could have put X in the home time, and then that driving there would have been X plus 1. Either one would be fine. All right, so the distance driving there is 40X, and the distance driving home is 48 times X minus 1. Okay, and again, we're always going to multiply those first two columns together to get that third column. All right, now what scenario do we have? Going back to our three different situations. Is it same distance, opposite direction, or same direction but different distance? Well, in this case, the distance is the same. Okay, he's driving to his grandmother's house and then he's driving back. So the distance is going to be the same. Okay, and you always want to look for that first. But in that situation, you're going to set the two distances equal to each other. Okay, so the distance driving there, 40X, is the same as the distance driving home, which is 48 times X minus 1. All right, so as we solve, going to get x equals 6. Okay. All right, now, what did the question ask us to find? It says, what is the distance between Dr. Strangelove's home and that of his grandmother? Well, if x is 6, what did we really just find? We really just found his time driving there. Okay, that's what x represented. This over here is a distance. Okay, in fact, these distances are the same, so we could go to either box and plug x in, but it's going to be a lot easier to do it up here. So the distance then, to answer the question, is going to be 40 times 6, which is 240 miles. Okay, and so that's our answer for number 2. All right, for number 3, it says Miss Taylor and Miss Backus leaving their cars from the same location at the same time, traveling in opposite directions. Miss Taylor travels 8 miles per hour slower than Miss Backus. After 4 hours, they are 368 miles apart. How fast was Miss Taylor driving? Okay, so I would encourage you to pause this at the point that you want and try to do as much as you can on your own. And then seeing what I got. Okay, so let's fill in what we know, okay? So Miss Taylor drives 8 miles per hour slower than Miss Backus. Let me label this. We'll have Backus and Taylor. And Miss Taylor is driving slower. So she's going to be x minus 4. Backus will be x for the rates. And then it says after 4 hours, they're 368 miles per hour. So, I'm sorry, 368 miles apart. So they have both driven 4 hours. So their time is 4. So Miss Backus's distance is 4x, and Miss Taylor's distance is 4 times x minus 4. All right, so of our 3 scenarios, what do we have? Same distance? No, we don't know that. Opposite direction? Yes. Okay, this is a situation where they're going away from each other. So, and that means that the equation is we're going to add their distances together. So 4x plus 4 times x minus 4 equals the total distance apart, which is 368. Okay. All right, so we solve this equation. And x comes out to be, let me make sure I did this right. It's 48. Okay. And the question was, how fast was Miss Taylor driving? Okay, well, Miss Taylor is, we set her up as x minus 4. So we just found that Backus is driving 48 miles per hour, which means that to answer the question, Miss Taylor is driving 44 miles per hour. And that's it. Okay. All right, so I included one more example on here. Again, if I would suggest that you pause this and try this all on your own and get as far as you can before I go through it. Okay, so as we fill this out, which again, remember only looking at rate and time for this. So probably the easiest part is that we know that Jack goes 12 miles per hour and Jill is 16 miles per hour, okay? All right, so the time is a little weird. First of all, it says that they're getting ready to leave at the same time, but then Jack, or I'm sorry, Jill has a flat tire. All right, so Jack goes ahead and goes, but then Jill has to fix her tire, and then she has to catch up to him. Okay, and so it takes her 15 minutes to fix their tire. So let's say that Jack's time is X. then since Jill has to wait 15 minutes before she goes, we have to subtract that time. Now, here's the deal with this one. We need to be very consistent with our rates, okay? And rates are given in all our units. We need to be consistent with our units. And rates is given in miles per hour. So that means that our time and our distance units need to be in miles for distance and hours for time. So we don't want to say x minus 15 because 15 is in minutes. Okay, how much of an hour is 15? Well, it's 1/4. Okay, so we're going to say x minus 1/4 or x minus 0.25 if you want. Okay. Sometimes if you have a weird conversion, if you're just converting time, then just put it over 60. So you could do 15 over 60, but of course that reduces to 1/4. All right, so Jack's distance is 12x. Jill's is 16 times x minus 1/4. Now, in this case, they are going the same distance. Okay, so they are going the same direction, but what's more important is that they're going the same distance. So we're going to set their distances equal to each other. 12x equals 16 times x minus 1/4. All right, so solving this equation. We get x equals 1. Okay, and so it says the question that we're answering is how long does it take Jill to catch Jack? Okay, in other words, and what I mean by that question is once Jill starts to ride her bike, how long does it take her to catch up to Jack? And so we're going to go to Jill's time where we have to plug in 1 for x. So 1 minus 1/4 is 3/4. Okay, and you could write your answer one of two ways. It's fine if you write 3/4 of an hour. Okay. Of course, you also probably know that 3/4 of an hour is the same as 45 minutes. Okay. So if you want to go ahead and convert that to minutes, that's fine. Doesn't really matter to me either way, but that's how you would solve that problem.